do I need this one, right?
No, you don't need it.
Nobody needs it.
It's up to you.
Okay, I think my voice is usually too big. So, something I want to talk is a bit different from this mainstream of this conference because it's more related to gauge theory than mirror symmetry. But I think Floer homology of divisor complement should be related to mirror symmetry. But the interest of me is a bit kind of away from the interest of the mainstream of the people. Okay. Now, I want to explain one baby problem, or some baby version of the problem I am really interested in. So the situation is the following. Suppose you have some X symplectic manifold, which let us assume is compact. And you suppose you have a compact Lie group acting on this symplectic manifold, which is a Hamiltonian actions. And we assume that G has a normal subgroup G0, and the quotient is G bar. And we take this symplectic quotient of X with respect to this G0. So it means that you have this moment map. So the original moment map mu is go to X to G star, and then you divide again. So you can just take quotient of G0 star, the moment map of this G0 actions, and you take U0 inverse 0 divided by G0. And I assume that this X bar is smooth. So action of G0 of this U0 inverse 0 is smooth. But I do not assume the action of G is smooth, is free. So you have a fixed point of this G, but do not have a fixed point of G0. So X bar is a smooth symplectic manifold. And I consider two G invariant Lagrangian submanifold of X, which is contained in the zero set of the moment map. Then it induces Lagrangian submanifold of X bar, which is G bar invariant. So that's the situation. So this is something like a relative version of a symplectic quotient problem. And the claim of this baby theorem, baby situation, is the following. So we consider this Lagrangian Floer theory of this two Lagrangian submanifold, which is above on X. And we consider this G equivalent version of Lagrangian Floer theory. And then you consider this quotient L1 bar and L2 bar, and we consider G bar equivalent versions. And the claim is after something called bulk deformations, they became isomorphic. And there is a correspondence between bulk deformations. It goes from equivalent homology of X to G bar equivalent homology of X bar. And this is some kind of a relative version of Chris Woodward's quantum Kawa map. So Woodward is the case when G0 is G. Yeah. So in absolute versions, Woodward corresponds to some map between these homologies. And then, so then we can just prove this kind of theorems. And
so does the map depend on L1, L2? The map B?
No, it's just absolute map. So suppose you have this kind of X and X bar with some G0 quotient. Then you have a correspondence between this ambient classes. And if you deform this Lagrangian Floer theory by ambient classes, you have isomorphism. Actually, one need to make it precise. One need to include some bounding chains, or assume that L1, L2 are monotone in that case. But somehow, in some way, we justify Floer homology, then the equivalent homology is isomorphic.
Can you say again what was Woodward's version?
Woodward's case is G is equal to G0. So the global symplectic quotient, the symplectic quotient is compact. Yeah. Yeah, I mean, to make it work. So the motivation is in the following things. So I want to consider something like a symplectic quotient of X by G. That is singular. So I want to consider this kind of singular symplectic manifold. And then I want to study Lagrangian Floer theory of it. And you know this symplectic topology, then the singular Lagrangian submanifold is very, singular symplectic manifold and the singular Lagrangian submanifold is very hard to handle. So the idea is just to go up and to do it equivariant. But then the problem is that there might be several different ways to take a quotient of the same spaces. And if you define a different way like this, but then equivalent homology is isomorphic. It means that this guy, it's more safely to say that it's a Lagrangian Floer homology of this singular symplectic quotient. So that is this statement means here.
Is this G equivariant homology a thing which is defined or a thing which is
yeah, that's something I want to say. So there is this quotation mark in the theorems. So first of all, G equivalent Floer homology is studied by many people, and there's a work by Hendrik and Sarka and Lipschitz, but that's some restricted cases. And I wrote some papers about construction of G-equivariant Kuranishi structure, a locally Kuranishi chart, that's 2 years ago. And I believe one can just go through to get this equivariant Lagrangian Floer homology, a complete generality, using a lot of bunch of things. So I plan to write it in a couple of years. And after a couple of years, the people start complaining, so I don't know when to finish. Anyway, so I have no doubt that I can define it, but once defined it, we have this kind.
But you'll need some sort of virtual technique.
Yes. I mean, equivalent transversality is harder than usual transversality. And many people study this finite group, for example, Cho and those people study this finite group actions, but the continuous group is harder. So you have some issue. And there are many things which I plan to define, but it's not yet defined. So now, and there are two kinds of proofs which you can do. One is this proof by Woodward and Kshu. And Woodward and Kshu wrote some papers which I think basically prove this kind of theorem in the case G equals to G0. 5 years ago there is some preprint. And one can do it using Lagrangian correspondence. So because that this set, x1y and x cross x bar, suppose that u0x is 0 and the equivalent class of x is y. So this is something like some manifold in the product spaces. And if you calculate easily, this is a Lagrangian sum manifold. And there is a general story that Lagrangian sum manifold corresponds to this, gives this infinity functor. And this infinity functor, and one can prove that it is a kind of give this equivalence. That kind of things I think actually I talked in some conference 2 years ago. In the case G equal to G0, and I'm still on the way of writing. So there are too many things to write.
So the B and the B bar are the bulk deformation that make the correspondence unobstructed.
That's right. There's for each B have a continuous B bar, so that is unobstructed. But that kind of things appears later on a bit more delicate situations. So
Equivariant Lagrangian means just Lagrangian preserved by the action?
yes, set theoretically preserved.
That's it.
That's it. So we have these theorems. And this theorem itself, I mean, compact group and normal subgroup is something like just a direct summand. So I don't know how much very interesting this is. But the real case I'm interested in is not this finite dimensional things, but it's infinite dimensional analog. That's something I want to explain. So that's gauge theory. So we consider sigma Riemann surface and G, so this Roman G. I'm sorry, but this is a slide. So my handwriting, Roman G and italic G is almost indistinguishable. But probably on the slide, the Roman G is a compact Lie group. And then this, italic G is the space of all maps. Now sigma to G. I want to use the same notation as before. So G is a gauge group, and this italic G is a gauge transformation group. It's a map from all sigma to G. Sorry. So X is a symplectic manifold, which is a set of all connections on trivial G bundle on sigma. And there's a very famous G axiom, and G0 is a so-called base gauge transformations. I'm sorry, this is Roman. Yeah. this is italic. So you have a gauge transformation, which is identity on a fixed base point. That is this G of 0. So now this is normal subgroup, and the quotient is a gauge group. This Roman G. So now there is a natural action. Connections is acted by gauge transformations, and this is a very famous story that this has a moment map. And the moment map is exactly the curvature. So you have connections, you associate a curvature. I do that. A is f of A, and the curvature is two formed value differential forms, and this is dual to the Lie algebra of this G. So that is this, and the symplectic quotient is very famous fact. It's a modular space of flat connections on your Riemann surface, and the modular space of flat connections on the trivial bundle is singular. It is, there are a lot of singularity related to so-called reducible connections. Typically, trivial connection is a bad singular point. So this singularity of the space of representation is a kind of major headache of this kind of so-called Atiyah-Floer conjectures and that kind of studies. So that is the main reason that I want to consider these cases. But then, so this is a singular, but you have still this kind of pictures. And I want to consider Li. It's a modular space of flat connections on handle body, HG, whose boundary is sigma. So you have this flat connection. So then I can show that this is a Lagrangian submanifold on this mu of the space mode connections. That is also a classical fact. This is the infinite dimensional Lagrangian submanifold, and this is the infinite dimensional simplex manifold. So now, so now we consider this Lagrangian Floer homology, equivalent Lagrangian Floer homology of this infinite dimensional situations. And this one is, we can naturally say, it's a kind of gauge theory version of gauge theory version. It's something like instantaneous Floer homology. You have these two Lagrangian submanifolds which correspond to the Hunter body, and you consider these intersections that give some kind of some modular space of flat connections on a three manifold which we obtain by gluing a Hunter body. And this particular version is not completely coincident to what Floer defined. It is coincident more closer to what this Salomon and Welfeld introduced in one of their papers at the beginning of 2000. And so this is something like, and I think one can now prove that this is isomorphic to the actual instant homology of the three manifold. So this infinite dimensional version should be gauge theory things. It's a kind of a space of all big connections, and you have a Floer homology.
When you say actually prove, you mean after you define this thing?
Yeah, this one is mostly defined. I mean, this one is defined by this by some small perturbation defined by these people, Salomon and Welfeld. And they are explaining how to prove it to go to the usual instant of the homology. So now I want to consider the situation. So I want to take this. Let's see. Yeah. So now then this is a kind of gauge theory. So we consider this simple quotient by G0. That's I explain what it is. And then you consider this Lagrangian submanifold. And what's nice is that they are this simple quotient x divided by G0 is a smooth symplectic manifold. And L0 bar, L2 bar, L1 bar, L2 bar is a smooth Lagrangian submanifold over this symplectic manifold. And this G, it's gauge group like SU2 or SUM, is G divided by G0. So you still have this finite this group. So this one, this big invariant, infinite dimensional equivalent gauge Lagrangian Floer theory is a gauge theory things. And this one is naturally regarded as the symplectic side of the Floer homology. So you have these two symplectic manifold, two Lagrangian submanifold, and equivalent version of Floer homology. So it's naturally a Lagrangian Floer theory. So we want to prove how they are related. And so suppose that this baby theorems I explained. So this one is a gauge theory version of Floer homology, and this one is partially symplectic quotient, is a symplectic side of Floer conjecture, which actually I was proposed with Alcaba Daimi in a couple of years, in 1 year before. And so now, if this
the X mod G0, that's now finite definite,
yes,
kind of framed.
Yes, I'll explain what it is. So if this infinite dimensional analog of the theorems I just claimed is correct, then it implies that they are Floer conjecture. So that's why I'm so much interested in this baby theorem. And I don't know in a finite dimensional case if there's any interesting application of this baby theorem, but this infinite dimensional case is very interesting. So that's a kind of motivations of this whole story. However, as you can guess, the story does not look so much kind of easily. So there are many things you have to think about it. So the issue is that what is this symplectic quotient? So so we consider this curvature map, but then you just take quotient to this G0. So you want to take this U0 inverse 0. And what you can think that G0 is a gauge transformations, which is identity on P. So when you take this moment map, so you just kind of all the maps but except P. So the naturally, kind of morally, you can say that this mu0 inverse 0 is a connection A, which is flat outside of this particular point P. Because you have G and G0, the difference is a kind of value at P. So you can kind of believe, think very naively, this is what you are. But of course, this is not so much a correct definitions. You have any smooth connections, it's flat outside one point, it's flat. So this is something which looks kind of morally correct, but it's not correct. So you have to do something to understand what it is. And the natural thing is the following things. So we consider this modular space of flat connections on the sigma minus p. So you have a flat connections which is flat outside of p, and you consider some kind of monodromy behavior. So this is something very similar what this Kronheim and Broca are doing in these 4 dimensions. They consider codimension 2 submanifold and study ASD connections outside of codimension 2 submanifold, and they work out very strong theorems. So this is 2 dimensions. It should be easier, but still. And this kind of modular space is called extended modular spaces, and it is studied by Heinrich Symplectic geometry, Jeffrey, and those people. And this algebraic geometry, this Webersman and Manesco and Woodward are the person who proposed to use this thing in these problems. So I just want to explain a bit more about this thing. So I want to explain 2 descriptions. One came from algebraic geometry, and the other came from symplectic geometry. So I want to explain this from algebraic geometric point of view. And so let me consider the special case that your group, gauge group, is SUM. Then we consider this triple E, P, rho, and E is a rank n holomorphic vector bundle on your Riemann surface. So you have a complex structure, integrable complex structure, and the P is a trivialization of the determinant bundle. So this means that E is somehow SL2, SLNC bundle. And the rho is a plane at one point of this E. So you fix framing. But this framing is SLNC framing. You have determinant rho is this trivializations. So you have this triple, you have a holomorphic rank vector bundles, trivialization of its determinant bundle, and SLNC framing at one point. So this triple, and you can imagine that the modular space, you can see that kind of isomorphism. And the modular space of such a triple is naturally a complex manifold. And people study these kind of things, like Webersman, also already Sechardri and those people study some, this is a special case of those people studying. And yeah, so this is an isomorphism. And we have this SLNC actions, we just change the framing. And what is known about these people is that this complex manifold is a quasi-projective variety. Of course, to do this kind of business, we need to define some kind of stability conditions. So probably we need to require that this triple is stable. Then there's the modular of the stable object, you can compactify naturally, and you get a quasi-projective variety. So it means that this guy is a complement of some compact Kähler manifold, compact projective algebraic variety minus normal crossing divisor. So that is known in algebraic geometry. But the issue is that, and also we can do it equivariantly. So you have this kind of, at least in the SUNC action, so you can just compactification has a SUNC actions, so that everything is invariant. However, the problem is the choice of these compactifications, and I think basically nobody knows how to compactify in a canonical way. So it seems likely that there is no canonical compactifications. So you have a quasi-projective variety, so we know that it exists some compactifications, but it is kind of not canonical. There are many possible ways, and there is no particular way which one we choose.
Okay, so R hat is the space of framed stable bundles.
Yes.
So it's algebraic geometry.
Yeah.
So the definition of that already includes a stability condition.
Yes, I think so.
So
Then you can compactify using the stability condition. And the choice of stability condition is not unique. That's a problem. There are many different ways to define stability of this kind of object. And that's I think in algebraic geometry knows about many things about it. It's like highly non-trivial problems. And they say that there are some stability conditions so that you can make it projective. But the choice is not canonical. Okay, so now this is the algebraic geometry picture. And you want to construct a complex structure on this spaces. It's rather immediate. But you want to define simplex structures. You just look at this and it's not so much obvious. And if you know how to compactify it, you can project algebraic variety, you have simplex structures. But that simplex structure is not so visible. So now let me go to this symplectic side. So this is the kind of work by Jeffrey and those people, and which maybe many people are more familiar with. So we consider a pair A and C, and A is a flat SUN connections on a trivial bundle of sigma minus P. And Xi is some element of the Lie algebra of SUN. And you fix r theta, a polar coordinate of this particular point P. Then we require that Fa is this Xi times d theta is this S1 direction, and on this neighborhood of P. So we consider this kind of things, and we have natural gauge transformations which is kind of constant in the neighborhood of P. Identity. Yeah. Then we have this modular space of such objects, so we kind of pair of A and Xi as this. So that is another things. And what is known about this space is the following things. So we consider mu from this space to the Lie algebra, just send this Xi to Xi. And what is known by this Jeffrey and those people is that this space is has a symplectic structure on the neighborhood of the mu inverse 0. So if you go far away from mu inverse 0, this simplex structure may degenerate. But at least on the neighborhood of 0, you have honest groove invariant simplex structures. And also then there, this mu is actually a moment map of this SUN actions, and this simplex structure is invariant. So this is a nice symplectic structure.
Can you remind us what Xi is, sorry?
Pardon?
Can you go back one slide, so
Yeah.
let's see what Xi is.
Xi is a monodromy around the punctures.
Thank you.
So now we have this kind of situation. You have these these symplectic things and the complex things, and you have the neighborhood. And so then my frame is that this in the neighborhood of this zero set, and here you just consider the case when this rho is a framing. This framing is in general this SL and C framing, but you may require that this one is a unitary framing, SUNC. So this subset, and then I claim that this neighborhood has kind of canonical diffeomorphism. The construction is the following. So we have this element XC, which is an element of the symplectic side of these compactifications. So we just usually decompose D plus A as a dA plus D by A. It's a kind of 1, 0, and 0, 1 part. And you can just use usual equations, D by H equals 0. So this defines as usual is a holomorphic structure of the trivial bundle outside of a point P. So you have a P and you have flat connections outside of P. It canonically induces a holomorphic structure of these trivial bundles. But then we want to extend this this holomorphic structures to this to the point P. And the way to do it, we use this Xi. Sorry. So this Xi monodromy you can diagonalize. So you have some basis. It's a kind of diagonal matrix. Then you use how the A called Xi d theta. Then this E1 to En is a kind of gives you a multi-valued flat sections. If you rotate once, then this frame is a kind of has this monodromy, right? 2 pi I alpha 2 pi I alpha n. So you have some multi-valued framings. So this framing is not so good. So I want to cancel this framing by taking this g to the power minus alpha m e of m. So this is a holomorphic functions. So, but this diverges to infinity, but you still have a kind of you have this holomorphic frame, which is a kind of local frame, which is a very globally defined holomorphic frame, which is defined single varied holomorphic frame in the neighborhood of P. Then you can extend your bundles to P by just requiring this frame to be the frame at that point. And together with this, so this is the SLNC, so this sum is 0, so you have this SLNC framings and this complex vector bundles. So starting from this data, this A and Xi, you can end up with this triple of this holomorphic vector bundle, SLNC framing, and trivialization of determinant bundle. So this is a map, and this should be a diffeomorphism. But the issue is that something like very similar to the usual case. You have a compact. You consider Riemann surface without any punctures. Then you consider modular stable bundles and modular flat vector bundles and this Nonuniqueness shadowing theorem, so that they are isomorphic. And then from this complex algebraic geometry pictures, you get the complex structures, and this symplectic pictures, you get the simplex structures, and they together give the Kähler structure. That's a kind of natural story. And here we have a similar story. So in this neighborhood, I didn't calculate, but I have no doubt that this gives somehow by these identifications, this simplex structure and this complex structure kind of match together to get Kähler structure on the neighborhood of mu inverse 0. But the issue is that this is non-compact. So you have some non-compact simplex manifold which contains this mu inverse 0, and then you have this. Then you need to you need to find some compact sympact manifold so that you can do Floer theory. And the lesson from algebraic geometry is that this compactification is not unique. So how we can do it in the symplectic side, and we can do it in symplectic side, but still it is not unique. So in a symplectic side, what we can do is, so, but anyway, before that I want to consider following things. This is just a review. So in algebraic geometry, your modular space is written as a complement of projective algebraic polarity, smooth projective algebraic polarity minus normal crossing divisor. So that is the symplectic side of the story. And and this is unique actions. But not unique, this compactification is not unique. So symplectic side, what one can do is the following thing. So we have this moment map, mu to this symplectic domain to this SUN. Then we just compose, but this has a symplectic structure, but it degenerates if you go far away from the image of, from the inverse image of 0. So you just try to do Floer theory, then you can do it in a neighborhood of mu inverse 0, but if far away, symplectic structure degenerates, so from a business has a difficulty. Then what we can do is that you compose this one, this moment map with quotient of this adjoint action of SUN, and the quotient is famous. This is very famous fact. This is so-called wild chamber. Then there is constructions which is called symplectic cut. You take some appropriate polygons on this wild chamber. It's a kind of wild group equivalent polygons on this real algebra of the tori. Then you just consider this inverse image. So what happens? Then we can get some, so this kind of things, and we take these polygons, and we can compactify the inverse image of the interior of P to get some y prime, and the d prime is the image of this boundary. And this guy, then this guy y prime is a compact symplectic manifold, and u prime, there's the SUN actions, and u prime is just this moment map, and its image is just this original map. So I mean, you take this inverse image of the interior of the polygons, you can obtain some divisors to the boundaries, and what you get is a compact symplectic manifold of which this groove acts, and the moment map is mostly the same on the original one. And if you take this polygon enough small, then this original symplectic structure is smooth, is non-degenerate. And this is called the non-abelian symplectic cut, and this is also Chris Woodward studied this kind of things, and there are several other works. And then we are in a situations that you have this kind of, again, you have compact symplectic manifold and divisors. And you have group actions. But the issue is that this symplectic manifold, again, depends on the choice of polygons. So there are some conditions about the polygons, which have some nice property about this boundary wire chambers. But the choice is not unique. For example, you can blow up somewhere. And the choice is, so we still have this compact symplectic manifold and divisors. But this choice is, again, not completely canonical. You have some ambiguity. So what we are doing with algebra diamond is the following things. Suppose we have a compact symplectic manifold and D is the normal crossing divisor. And so Y is a compact and smooth symplectic manifold, and you have a normal crossing divisor. And you have a compact Lie group G acts on it. And you have a moment map. And suppose that P is this image, and the boundary is a kind of this divisor. And that Li is a Z invariant monotone Lagrangian submanifold on this divisor complement. This is mu inverse 0, so it's not yet of D. Then in this situation, what we can do is that we can prove this, define this equivariant Lagrangian Floer homology between these two Lagrangian submanifolds. So this is a bit more dangerous than just the just equivalent Lagrangian Floer theory. You have this divisor complement things, and maybe 3 or 4 months before, Riccobodami and myself uploaded some manuscript. And what proved this kind of thing in the case G is trivial and D is a smooth divisor. So in that case, you can define Floer homology, but we have to go much further to include all non-trivial G actions and all normal crossing divisors. We know how to do it, I believe, but it's a kind of a work of 3 or 4 years. So. Yeah. So now this is something we did. Maybe I need to mention that this Y minus D is a non-compact symplectic manifold, and this one is not tailed or not convex So in general, at infinity, if you put any reasonable Riemannian matrix, then there is something called a collapsing Riemannian manifold. So and there is a kind of no injectivity radius bound. So this doesn't fit in a story that many people study. Usually, for non-compact simplex geometry, most of the people study something like complexity or kind of tameness. Then compactness is okay. However, here this one is a kind of very highly non-compact. So you have some series of harmonic spares or any harmonic curve which just approaches to this divisor D. So there is something new. We need to do this to work it out. Okay. So now, so now this is a kind of candidate we can try to define sympathetic side of this Floer conjecture, or at least in this kind of G-equivalent patterns. But then the problem is, as I said, there is a non-uniqueness. So as I said that in our situations, this on my main interest, your kind of space of flat connections, you can represent as a simple quotient of something smooth, but then this smooth one is in general non-compact, and you compactify it, then the compactification is never canonical. But something which might be good is that kind of D is away from this L1 and L2. So I want to ask one question. So the problems, and this is very interesting. At the beginning, a couple of months before, I thought that this is okay, but it's nasty. So it might be even answer is no. So the answer is the following thing. Suppose you have two simplex manifold, compact simplex manifold, smooth compact simplex manifold by I, and the di it's normal crossing divisor, and we assume there are z actions and its moment map by I to gate, and pi is a moment polytope, and di is its kind of inverse image of the boundary. And suppose that there is a neighborhood of u1 inverse 0 in y1 and u2 inverse 0 in y2, so that everything, including group actions and symplectic and form, is a completely isomorphic. And your Ly is a Lagrangian submanifold in this u1 inverse 0 and it also u2 inverse 0. Then, in this case, this equivalent Lagrangian Floer theory is isomorphic or not. So it depends on the choice of compactifications or not. But that's something which looks correct at the beginning, but it's a bit nasty questions. So I have a few remarks. This conjecture, this problem is positive if this yi minus di is convex or tame. Because in that case, you have a kind of Lagrangian submanifold away from the end. Harmonic disk never approaches to this divisors, so you don't have to worry about it. So infinity does not play a role at all. So this is a kind of well-known fact. And the second case is, this is a bit more delicate. One can prove that this is correct if y2 d2 is a deformation of y1 d1. So it's a kind of, it's a topologically, something like as a differential topology, if these two guys are the same, and you deform the complex structures, if you go one to the others, one parameter family of deformations, then this play homology is independent. That we can prove. This is not trivial. It's a part of the construction of this. You can prove it. So the more serious thing is that something like you have the situation is something like this. You have something in infinity, and you have a L1 and L2 here, and you try to calculate Floer homology. Then your disk is something like this. Then if you add, if you something like take a blow up here, and you have some new component, then whether this process changes Floer homology of this guy or not. And if this disk never approaches to these divisors, of course this is okay. But in our compactifications, it's kind of rather delicate compactification, so that everything may have escape near the neighborhood of D, and we have to some delicate process to to eliminate it. So potentially, it depends on how this blow up occurs. So this is the second case. But one can prove that, what one can prove is that something which escaped here occurs in a kind of codimension 2. So if you have a one parameter family of deformation, this codimension 2 things just imply that there is no change. But if you have this kind of discrete change, something like topological change, then this kind of argument does not work. In the third case, this is true, is that if this one is okay, if this this part is actually is free. So the moment map, if the moment map is kind of transversal to 0 and action is free, then we can prove it. And the proof is just like this. So suppose that this is smooth and G action is free, then you can consider this. You can take this symplectic quotient of y2 and y1 by these G actions, and you have a compactness manifold. And there is a theorem which is kind of similar to this Woodward's Xu, and we proved is that this one both are isomorphic to something you see from the quotient. So they're both equal to this, so they are isomorphic. So that's a proof. So the issue is that something like whether this is so these three cases is good enough to define to convince that this is very defined, but I don't know. It might be even the case that it is not invariant. So the one reason is that so the summary is symplectic side material Floer conjecture for any G is certainly equivalent version of Lagrangian Floer theory of this. But then this is singular, this space is singular, and it is written as a symplectic quotient of something smooth, and then we can realize it as a kind of Lagrangian equivalent Lagrangian Floer theory of a divisor complement of the smooth things. However, we do not know that it depends on this compactification Y or not. So that's the situation. Now, but then there is some exceptional cases. If G is SU2, that's actually the original case that your Floer studied. And in this case, actually, we have some canonical choice of Y up to deformations. So in this case, I still believe that there is somehow very canonical way to define it. So why it is? So let me consider this case, simple case, G is SU2. Then the moment map goes to this SU2 divided by conjugate action of SU2. This is just an arc. So the choice of polygon is almost nothing. It's just a kind of half open interval. so all the difference just reduces to these epsilons. And as I say that we have a one parameter family of deformations. The Floer theory does not change. So you change epsilon, you have still the same thing. So this is the kind of exceptional case. We may expect that this symplectic side is very defined. On the other hand, if you go to gauge theory side, so we consider this instanton Floer homology of X with trivial band M, 3 manifold M with trivial bundle G bundle G. Then the Floer himself defined instanton Floer homology in the case of this gauge group is SU2, and the manifold is a homology sphere. So that's what Floer did something like 35 years ago already, right? Ancient time. But what Floer did is a bit different from equivariant homology, because Floer's case, he just thrown down the trivial bundles, kind of fixed point. But you can include fixed point in a usual way as equivalent homology people do, and that pattern should work. And so in these cases, in homology spheres and this SU2, we may expect that equivalent Floer homology is defined. I think it is already defined, but I don't remember so much precisely. So now, but you go to beyond SU2, like SO3 is okay, but you have much bigger group. Then Kronheim and Rofka define some version of instanton Floer homology, which is not equivalent version. It's something related to this non-equivalent version of this instanton Floer homology. That is defined. However, in a general G and equivalent version, I think nobody yet knows how to define it. So before I come back to gauge, I think I thought this kind of thing is already known, but then I talked with several people, especially my collaborator, Maria Koddaimi, and now I understand that this is not yet understood. And one difficulty is again this kind of non-compactness. So the vector space, so the space we consider is something like a space of all connection. It is flat vector spaces. But as you know that there are still non-compactness. If you consider modular formal curve, that's similar to this anti-dual equations. There's a bubbling. So there are something going to escape to infinity. And I think the most big difficulty is the following thing. So you consider this gauge theory on M cross R. This is 3 manifold. Then we take this some particular point P. I mean, this is a frame theory, so some particular point P. Then this point P is something like you take this framed gauge transformations. Your gauge transformation is assumed to be trivial on this point. But then the trouble is that there are a lot of points you may bubble. it's almost always okay, but if your bowering happens on this particular point P, then this framing things is a kind of completely breakdown. So you have this kind of G actions on this, using this special line, where your gauge transformation is assumed to be trivial. But then, if the bowering happened here, then everything became too much chaotic. And this is, I think, as I understand, the main difficulty to define this equivariant Floer homology. So that's something related to this non-compactness of the time space. So I don't know what's a nice way. So I think most of the people just believe that this kind of equivariant Floer homology is defined for complete general G. Just we are not strong enough to do these technicalities. But after kind of this uniqueness of the Lagrangian side, symplectic side, I am beginning to wonder it might be the case that this for general G in standard Floer homology may not be very defined. It depends on some choices. So that's something I don't know. So the gauge theory side. And there is some versions which uses some non-trivial bundle rather than trivial bundles. There are some cases that some variant of this homology is well defined. That's called admissible bundles. And that corresponds actually to this case, is that this kind of moment map image is smooth and reaction is free. So in that case, it's like I saw 3 bundle with a non-trivial W2. Kind of instanton side, Floer homology is defined. And we can prove this kind of uniqueness using this case. So the story looks somehow match. So how this non-compactness, symplectic geometry side and non-compactness of this gauge theory side matches. So now I want to explain some speculations and some partial results which is related to this kind of things. So suppose this conjecture, this problem is negative. And suppose we are in a, so I still do not have any example that this equivariant Floer homology depends on the choice of compactifications. But suppose that it is not well defined. So what is true is actually something. Yeah. So then I can try to explain something. So this is kind of a first baby theorem, right? Kind of x bar is a simple quotient of x, and this bulk deformed Floer homology above is another bulk deformed Floer homology below. So now, if this is not true, maybe we can just include again this kind of bulk deformation things, so that after particular deformations, we still have a very definedness. So we may include this deformation parameter so that this is okay after deformations. So what is this deformation parameter? In a usual compact cases, deformation parameter of Lagrangian Floer theory is a cohomology group of ambient symplectic manifold. That's called bulk deformations. You have any even degree cohomology classes of ambient symplectic manifold, you can use it to define the whole Lagrangian Floer theory. That is called bulk deformations. And Woodward's quantum cover map is this map between this parameter. So now I want to consider the case of the deformations of this some variant. So we have this kind of x and d. X is a compact symplectic manifold and d is a divisors. And there, so in the case when x minus d is convex, there is something called a symplectic homology. And it is known that this, I think how much known is I don't remember. The symplectic homology is a deformation parameter of Lagrangian Floer theory of x minus d. At least this kind of wrapped category is a kind of all these bulk deformations coming from the symplectic homology. So, but then, actually, we have some variant of this symplectic homology. In the case D is not convex. The difference is something I think related to what this Gross and Zibet is doing. So I think Mark Gross sometimes explained that kind of, if you go beyond the convex cases, you need to invert this parameter called Q. The symplectic homology, X and D, and these are convex. The symplectic homology of X minus D is something I think the homology of X plus I think homology of S1 boundary over D cross some formal parameter. Right? This is kind of smooth divisors. This Q is formal parameter. It's nothing with energy. It's another formal parameter. It depends how much it rotates around these divisors. And what Gross explained and Gross and Siebert is doing that we need to include Q and Q inverse to make this kind of things work in the case when D is not convex. So it's kind of positive thing is not enough. You have both positive and negative things. And that also studied by the people of this so-called Rabinovich-Floer homology. In the Rabinovich-Floer homology, they have similar things, and they have a kind of positive infinity and negative infinity. And that's something we expect we can do it. And if you look at a paper with Dani, we know the series of conjectures, how this kind of parameter should be in the case of this divisor complement, whose divisor is not necessarily kind of positive. So you have a kind of, you have a kind in bar, you have a kind of formal polynomial series. So now suppose that this is done. So I'm sorry that this is again kind of a couple of years of work. So this is a little conjecture. So first we need to make a divisor complement and equivariant, and then include non-compact things and this deformation parameter by some variant of symplectic homology. Okay, let me assume all is done. But 4 or 5 years later, then we consider the following situation. Suppose you have two polygons, so P1 and P2 on this quotient. Then we obtain this Y1 and the Yi di. So you have these two different choices of these compactifications. You have the two polygons. And once, yeah, so the simple example is you have this kind of X and Cn. You have the complex vector space, and it's just S1 action. Moment map is just the positive integers. So you have this R1 and R2. So you have these two projective spaces with different area. So that's the kind of situations that you have these two different polygons. This is kind of very, very case. So now, what I want to claim, not claim is conjecture, yes, not claim. Yeah. So conjecture is the following things. Suppose that you have this some bulk deformations which lies in some variant of symplectic homology of the big things, and then you have a variant of this bulk deformations on this another things, so that with this bulk deformations we can actually have an isomorphism of a Floer homology. So that is a conjecture, and the remaining 5 minutes, yeah, I want to prove the conjecture. And, and this is yet a conjecture, and it is a bit too much, you know, kind of, because just to state the conjecture, I have to write 5 or 6 papers and 1,000 pages. So. But I think I believe one can do it, then one may try to work out this kind of argument. So the proof should be something similar to this. So the situation is something like this. So let me consider this, right? So let me consider very simple cases. I have a kind of Cn, and moment map go to R, S1 actions. Then you have a R1, smaller than R2. Then you consider this ball of radius R2, and a symplectic cut. So its boundary is cut by S1 actions. You have this projective space, which is kind of this R2, and you have another projective space, R1, right? And then this symplectic cut process, you have some kind of a Lagrangian, you have some Lagrangian correspondence, which I can draw in this way. So you have this kind of a product. So this is you have this R P and R1 cross P and R2. So this side is R1, and this side is R2, and you have some Lagrangian sum and ball. Maybe I write minus. So this is something like a closure diagonal. So I mean, away from this boundaries, this is something like just a disk of this area. So you can just take a diagonal here, and you take a closure. And one case is that this is actually a Lagrangian sum and ball. So let me write this there. So now, what is so I want to consider this Rapt Floer homology. So I think this is the convex element. So Rapt Floer homology of this delta delta, and the symplectic homology of this P1 of this minus this divisor. And I just claim that this is isomorphic. So roughly speaking, this symplectic homology has two kinds of generator. One is kind of related to interior, and the boundary is something like this Leb flow. And it's kind of, you have a base point, so Leb flow is S1 bound over this projective space at infinity. So this one is basically homology of disk plus homology of Sn2n minus 1 with formal parameter. And this one actually topologically is I think is a disk. Because of this kind of, here you shrink by S function, but this one don't have shrink by S1 actions. So in this case, so you have something like this kind of summary code is just a disk. The generator is something which is large in the interior, and which again is kind of has a neighborhood of this boundary. You have this wrapping, and the wrapping gives so this again gives the homology of D2n, and this homology of S2n minus 1, and this wrapping gives Q. So they are basically the isomorphic. So what it implies? So then how imply the following things? So I want to use this fact that this Lagrangian correspondence, this projection is isomorphism, so that if you have any obstruction class obstruction here, you can put this bulk deformation to cancel it, because you have enough room from here. So it implies that after appropriate bulk deformations on this side, you can cancel all these obstructions, so that your diagonal is actually unobstructed. So if it's true, then this diagonal gives a factor from this big thing to the small things.
This relied on one thing being smaller than the other.
Yes, so that P1 is smaller than P2.
But in general, there seems...
Yeah, but I think one can replace P1 by proportions, but make it smaller. So it's continuous deformations. So my feeling is that this kind of ways you can have some system of this morphisms between these compactifications. And so this is a conjecture. So this is a proof of conjecture. So, so you need to believe me. So it's just too much things to be done. But then after this, probably you have this kind of inductive systems of this possible deformations, and you together with this, I think Zeber's kind of in Monday that they have some ideas to construct this ring structures, and that's a kind of this kind of system of all blow-ups and kind of very huge groups. That's somewhat similar to this, but this implies probably we have some kind of this guy is a correct parameter to deform on this compact line summary side. Then the Floer conjecture, you go to this gauge theory side. Gauge theory side has again this non-compactness, and I don't know whether there's a canonical way to get this to obtain this well-defined equivalent to gauges instanton Floer homologies. It might be related to these things. So that's this might be even more interesting, right? If you just kind of prove something is isomorphic, then but this has some kind of more freedoms, and it might give some insight of how this gauge theory is. Okay, I stop here. Thank you very much.
Any questions? Ben?
I mean, would you typically get on gauge theory side of this wall crossing phenomenon?
No, it's not wall crossing phenomenon. So if you want to define so equivalent Floer homology, first you study something about the kind of framed gauge theory. Then you want to see that kind of the framed modular spaces. You have some map which is related to this how this framing moves on this particular point. You take framing. This map may jump at the point when this kind of when bubbling up occurs.
But
so
this leads to wall crossing. This leads to wall crossing.
I don't know how much it is done, but it's something similar, yeah. So kind of, I think several people try to define this equivalent instanton Floer homology in complete general G, and people failed. As I think Kroheim-Novka's idea is to take some connected sums and to kind of non-equivalent versions, just what frames things, and that works. And they construct some what they call not Floer homology somehow for many G. But then if they want to try to make it equivalent, then I think still it's open.
If there's no further questions, let's thank the speaker again.